All right. So we can start with our first introductory tutorial, the first morning session for this workshop. I'm Anuj Karpatne. I'm an associate professor in the Department of Computer Science at Virginia Tech. And as been mentioned, I'm also an alumni of Minnesota. I feel very fortunate to have been advised by Vipin at Minnesota. And it's always great to be back to this campus. Along with Professor Aryan Deshwal, we'll be for the next 90 minutes going into the building blocks of generative AI. We'll talk about the foundations, the historical journeys that we have taken to come to these modern Gen AI um, 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 models that are being used um, uh, in almost every aspect of our lives. We'll talk about the frontiers that lie at using these models for scientific use cases for accelerating sciences inspired by the Genesis mission. And we'll also talk about the role of scientific knowledge in advancing the science of AI, as Vipin mentioned, the science of Gen AI. Um, um, so uh, Both Aryan and I would be going in and out, and we'll be covering different portions of this introductory tutorial. I'll start with the first part of this tutorial, which is the foundations of generative AI. And you would notice that some of these slide content for this tutorial is similar to what we discussed at the August workshop for those who were there last year. Right? Um, this time we are doing some deeper dives into models and their characteristics in Gen AI that is particularly relevant for scientific applications. We'll talk in more detail about diffusion models, and we'll do a deeper dive into how scientific knowledge can advance the science of Gen AI. So at a high level, right, if we want to describe the goal of generative AI, right, we are interested in building a distribution, a probability distribution of data samples. Right? Once we have learned this probability distribution, we can use it to generate new data samples. Right? And these data samples could be of varying modalities. Right? We can generate new text, we can generate new code, images, right? Modalities that you're more familiar with ChatGPT and other commercial Gen AI products. But we can also use the Gen AI methodology to generate new samples in various scientific applications. You can generate new molecules, new drugs, new polymers, and so on. And there are several um, generative AI models that are out there. We have just listed a few of the illustrative ones. Um, in this tutorial, we'll do deeper dives into their characteristics, their advantages, and so on. But here are some points that we would like to mention upfront. These are some of the salient properties that we would keep on revisiting in this tutorial, which are what makes modern Gen AI models particularly powerful for many applications. The first advantage of modern Gen AI models is that they are using learnable model structures, that they can learn from data, adapt their representations instead of using handcrafted structures. Another advantage of the modern Gen AI models that you're seeing on this particular slide is that they are blurring the boundaries between discriminative AI or predictive AI and generative AI. Right? Many of these Gen AI frameworks have been inspired by advances in discriminative AI, where we are interested in making predictions, but we are using their predictive power to also generate new samples. Another key characteristic of the modern Gen AI frameworks is that they're exploiting some form of structure in the data. It could be regularity in space, invariance in space or time, right? Or regularity in sequences, right? And We would discuss that how we can start from this building block of looking at structure or regularity in data, going beyond the domains of vision and language as we enter into scientific modalities, how we can exploit richer forms of structure, richer forms of regularity. So here is just conceptual figure to illustrate the different schools of thought or research areas that have inspired developments in modern GenAI frameworks. A longer discussion of these schools of thought are provided at the GenAI workshop that we had in August. So here is the QR code where you can go through that video recording. But you can see that there are these are almost like the headwaters of generative AI. We have ideas coming in from Bayesian frameworks that lead to Bayesian networks. There are ideas coming in from autoregressive models that have been historically implemented using ARMA architectures. There are ideas from energy-based models, latent space models, right? And all of these headwaters have contributed to the rivers of generative AI that we see today in these modern GenAI versions. And they all have nonlinear trajectories, right? They have interacted um, um, uh, together with other research areas. Um, and progress in all of these areas um, would have happened at a much slower pace if it was not for a few key turbocharging ideas of deep learning, which are highlighted here in blue. These ideas are central to how we have arrived at the modern GenAI frameworks. So let's go through each one of these three in slightly more detail. Right? So the first turbocharger of GenAI or modern GenAI is this idea of representation learning, that instead of using handcrafted features um, or, uh, or features that uh, are crafted based on our insights about the data. What if we can learn features automatically from the data? So this idea of learning neural representations and using deep neural representations has led to several advances, and they have roots in the classical frameworks of perceptrons going back to the 1950s. But with the advent of GPUs, the right hardware to facilitate their training and inference, and with the availability of large labeled datasets powered through uh, labeling efforts, large scale labeling efforts such as the ImageNet dataset, we have now observed the remarkable properties of these deep learning frameworks for automatically extracting features and outperforming many of the handcrafted classical machine learning frameworks that would use kernels that are sophisticated for a particular domain, or would use similarity or distance functions that are again handcrafted. A major moment or a milestone event was the AlexNet moment in 2012, right, when we found the remarkable ability of deep learning frameworks, convolution neural networks, AlexNet performing much better than state-of-the-art computer vision frameworks at that time. Right? And this led to the rise of many other predictive architectures, convolution neural networks, recurrent neural networks for time. Right? They're all exploiting different forms of structure in data. Right? But progress so far in these representation learning frameworks was driven by supervised learning tools. Right? So in problems where we had lots of labeled data, for example, the ImageNet dataset or the Brown University text corpus that was powering research in natural language processing. Um, in problems where we did not have the same scales of data, right? an important question to ask is, how can we still learn representations when we don't have labels? This is where this idea of self-supervised learning, right, leads to the next major revolution in deep learning capabilities, where we are still leveraging these predictive architectures, right, but using goals that are self-created. So in the absence of labels, right, even on unlabeled data, we can train these models on tasks that are that have cheap or inexpensive supervision. Um, for example, we can use these models to make predictions on its own tokens, or on its own portions of the data sample. We can explore them for reconstruction related tasks, right? And these ideas of reconstruction using autoencoders go back to the 80s. Or we can use them for next token prediction or next word prediction, right, which led to the BERT movement. So we can use these predictive models, right, even in the absence of expert supervision, to generate different portions of their own data sample. Another way to explore self-supervised learning is to employ contrastive learning methods, where we would exploit the similarities in the data samples, right, in some feature space. Another viewpoint, right, of thinking of self-supervised learning is what we now see in the form of diffusion models. These models have been learned to learn representations that are useful for denoising a particularly well-selected and a small amount of structured noise in the data samples. Right? So there are different ways, right, of creating cheap supervision, right, when we don't have labeled samples. And you would see that self-supervised learning, right, is really what helped us take these ideas of deep learning and representation learning out from the confines of supervised learning to learning with unlabeled data. But the third turbocharging event is this idea of learning models that are sensitive to the context of a particular data sample with other data samples in a structured sequence or spatial damage. These ideas of learning context-sensitive learning have roots in methods like k-nearest neighbors or local learning methods, right, where you're cognizant of the locality of other data points in your vicinity to make predictions. And the idea of convolutions, right, is also incorporating the local dependency, right? Um, what changed in 2017 with the coming of this transformer architectures is that we can now learn much more flexible models of capturing these local and global interactions among tokens. This is what we would call as attentions that can learn interactions between tokens or between different portions of the data sample automatically from data, um, and over sequences that are much longer than what RNNs or convolutions would enable us. So here are some of the directions that we have taken from the classical tools of generative AI to the modern versions of modern Gen AI. And you can see that we have these blue arrows that denote how all three turbocharging ideas of deep learning have enabled these advances. Um, uh, this is just one slide to represent how these ideas have come together. There is a longer discussion in the August workshop, but the key point to note is that these ideas, these frameworks that you're seeing in yellow, do not have to be considered as mutually exclusive. We can also think of going back to their historical roots and seeing how we can combine these ideas together. For example, can we combine the idea of learning latent space models, which are now encapsulated in the form of VAEs, along with using energy-based formulations in diffusion? So by looking at these historical roots, there are opportunities to create newer forms of modern GenAI frameworks. So with that, I would hand over to Aryan, who would talk about the characteristics and capabilities of GenAI for science.